But ultimately, one of the function of any expansion valve, as I added this, is by monitoring the temperature coming out from the evaporator, it is there to protect the compressor. We have to make sure we are superheating on this area. So we have to make sure whatever refrigerant we're sending into our compressor is completely gas. Okay? Because if we send even a very, very small droplet of liquid into a compressor, we will completely damage the compressor. Okay? You can't compress a liquid. You can only compress gas. And therefore, the only way to make sure what we send into the compressor is completely gas is to monitor the degree of superheat. So any expansion valve, regardless of the type and classification, it is there to monitor the degree of superheat. Okay, we've looked at what degree of superheat last week. We will also look at them as we go along. But by monitoring the temperature coming out from the evaporator, it makes sure that whatever is coming out from the evaporator is gas. So therefore, any expansion valve are there to protect the compressor, to make sure by monitoring the degree of superheat, we are sending only vapor into the compressor. So that's one of the functions. Okay, so to regulate the flow of the refrigerant, so therefore make sure we superheat when we come out of the evaporator, and therefore protect the compressor from getting damaged. One. But ultimately, the other primary application and function of an expansion valve is, don't forget, what are we coming out from the condenser? So at point 3, remember we said we have high temperature and high pressure liquid. And at point 4, we have low temperature and low pressure liquid. So ultimately, we have to use the expansion valve to reduce that high temperature and high pressure into low temperature and low pressure. Okay, that is the primary function, is to expand the liquid, therefore reduce the temperature and pressure. So when we go back into the evaporator, we are at low temperature and low pressure liquid instead of the high temperature and high pressure we are coming out of the condenser. Okay, now of course the next question I would ask is, okay, how does it reduce the temperature and pressure? How does an expansion valve, any expansion valve, operate? How does it do it? What is inside an expansion valve? I wonder if any one of you have asked that question before. What is inside any expansion device?
It's just a bottleneck, isn't it?
It's just a bottleneck. The word bottleneck, yes, but let's use maybe a scientific word for it. What is that bottleneck called in another term?
Fixed orifice?
Fixed orifice, yes. A venturi, an orifice, and a venturi and orifice, they use, so ultimately, so imagine these are a pipe, right? And all of a sudden, we are reducing the size of the pipe or the area of the pipe. Okay? So imagine you have pressure and velocity here, P1 and V1, and another pressure and velocity here. What do you think happens to the velocity here and the velocity from point 1 to point 2? If you suddenly reduce the area of the pipe, the velocity has to increase here. Okay? And Bernoulli's principle states that velocity and pressure are inversely proportional to each other. So if you're able to increase the velocity by reducing the area, actually you have area 1 and area 2 here. So if you're able to increase the velocity by reducing the area of the pipe, we are able to reduce the pressure. So there's a pressure drop here. So P2 reduces in that small area. Okay, so ultimately, any venturi or any orifice, uses the Bernoulli's principle. All they do is they constrict the area or reduce the area of the pipe, and therefore increase the velocity, but reduce the pressure. So we have a big pressure drop here. And if you reduce the pressure, what happens to the temperature? Reduces. Remember, pressure and temperature are directly proportional. Whatever you do to the pressure, temperature will always follow. So we are able to reduce the pressure here and therefore also reduce the temperature. Okay, and this is how any expansion device works. This is behind the principle of any expansion valve. By constricting or reducing the area of the area which the refrigerant passes through, we are able to reduce the pressure and therefore reduce the temperature. And therefore, if we go back to our diagram here, by having that venturi or orifice here, we are able to reduce that high temperature and high pressure. And when we come back to point 4, we are able to reduce the temperature and reduce the pressure. So low temperature and low pressure liquid. Okay, so we will look at some of the expansion valves, and don't forget, all of them have orifice or venturi, and they all use the basic principles of Bernoulli's principle by looking at pressure and velocity and area of a pipe. Function of an expansion valve is to regulate the flow of the refrigerant. Okay, and the way we regulate the flow of the refrigerant is by either using a fixed flow or a variable type of flow. So on one aspect, we're not able to react to the pressure of the system or the heating or cooling capacity of the system. It's very fixed. And the other types, we are able to respond depending on the pressure in the system, depending on the temperature in the system. We are able to vary the flow of the refrigerant coming in from the condenser, passing by the expansion device. So yes, again, we have a fixed opening type and a variable opening type. And those are the two types of classification method that we can use for expansion devices. Okay, so we will look at in a minute what we mean by fixed opening type and what we mean by variable. One is the capillary tube, and we will look at in a minute what a capillary tube looks like. And of course, the other one is an orifice. So a capillary tube, a very, very thin, long, narrow tube. A tube is the capillary tube that we use as an expansion device. The diameter of the pipe can vary between 0.5 millimeter to 3 millimeters. And if you look at the range, the length of the pipe, between 1 to 6 meters. And ultimately, again, all we're doing is we are using that capillary tube to suddenly reduce the area of the pipe. Okay, that small capillary tube. If you look at the advantage, so we will try to look at the advantage and disadvantage of the different types of expansion valves. Of course, this is just a very thin copper tube, so it tends to be relatively less expensive than the other types of expansion devices that we will look at. Of course, it doesn't have any moving parts, hence it does not require a lot of maintenance, and it tends to be ideal for hermetic type of compressors. And if you look at the disadvantage, of course, one of the disadvantage, as we said, it's fixed. It does not react or respond to what's happening in the system, to the pressure change, to the temperature change, to heating or cooling capacity of the system. So it's very, very fixed. So you don't have the flexibility of varying and controlling the flow rate as you would want to. Again, because of the size of the diameter of the pipe, it's very thin, so it's susceptible to clogging because of its narrow dynamics of the pipe. And of course, if you look at the other types of expansion devices, which are the variable, and There are few examples of the variable. The automatic expansion valve is one example of a variable opening, and sometimes it's called the constant pressure. Thermostatic expansion valve, I'm sure most of you have seen. And then we've got the float type expansion valve, which are very similar to the one that you have in your toilets, and electronic expansion valve. So we will look at some of these examples again, and we'll look at how they ultimately operate and where we have the Bernoulli's principle. So if you look at the automatic expansion valve, and also, as I said earlier, it's also called a constant pressure. So its primary function is to maintain a constant pressure in the system. And if you look at the expansion valve in itself, we will look at the different parts. So here we are coming in from the condenser. Of course, we're using strainers or a filter. And here we have a needle with a spring which reacts with the pressure differences. So here we have a diaphragm, very, very thin material, which easily reacts to pressure differences. So depending on either this pressure is higher or the pressure here is lower. So as you can see, so let's say if this pressure here is higher, we are pushing the needle up there. And coming back to what we said earlier, every expansion device uses orifice or uses the Venturi principle. So all of a sudden, as you can see, we are reducing the size or the area at which the refrigerant passes through. Okay, so therefore it's using the Venturi or orifice or Bernoulli's principle. Okay, so by using pressure, we are able to either push the needle down here, therefore we let more refrigerant, or by pushing the diaphragm up there, we are able to close that, therefore limiting the amount of refrigerant we pass through. Okay, and of course through here we've got going into the evaporator. So ultimately, as we said, the main principle behind it is that Venturi or orifice or the Bernoulli's principle, limiting or reducing the area at which the refrigerant is flowing through. So that's the same looking at the pressure differences and how it responds. And if you look at the application of AEV, as the name stands, is also called a constant pressure. So wherever there is a need for a constant pressure, therefore constant temperature, we can use that. Milk chilling units, water coolers, some examples that we can look at. They tend to be simple in design, and therefore, of course, compared to the others, it's economical. Okay, so that is another variable opening type, which is the thermostatic expansion valve. A thermostatic expansion valve, as the name stands, thermo means heat. So it monitors temperature coming out from the evaporator. So this is our evap. That part is what is in there. And of course, this is what we have in the expansion valve. So the whole part, and we'll look at it in a minute. So ultimately, we monitor the degree of superheat. We make sure everything we send into the compressor is gas. Okay, so that's why it's called thermostatic, because it's monitoring the temperature, the degree of superheat from the evaporator. We are maintaining a constant degree of superheat at the exit of the evaporator in order to make sure whatever we're sending is gas. We've discussed earlier, ultimately it's there to protect the compressor, to make sure slagging doesn't occur, to make sure we don't send any small droplets of liquid into the refrigerant. So let's look at how it looks like. Again, it's the same as the circuit that I've just plotted. So the filler bulb is, again, that is called the filler bulb. The one behind, you can see the bulb, a small bulb, and ultimately, as I've drawn it there, it is monitoring. So this is going into the compressor, so coming out from the evaporator. So this is your evaporator here. This is coming out, and using the feeler bulb, we are monitoring the temperature going to the compressor. So here you have your compressor. Okay, so what is inside the feeler bulb and how does it work? Actually, again, let's go back to the Bernoulli and Venturi's principle. So here we are coming from the condenser, and as you can see, we have our favorite word, our Venturi or orifice. Okay, and again, by using a diaphragm which easily moves depending on the pressure. So what happens here is inside the feeler, inside here, we have another substance or another refrigerant, okay, which boils depending on the temperature sensing here. We can easily boil this refrigerant inside here. So what happens is, as it boils down, the pressure in here varies. So we are either pushing the diaphragm down, therefore we're pushing the needle down, letting more refrigerant, or if the pressure difference coming out from the evaporator is higher, we're pushing the needle up, therefore closing the orifice more and limiting the refrigerant flow. So the fluid inside the bulb, it's called a power fluid, and often the fluid or the substance that we have here, it could be the same refrigerant as the circuit, the refrigerant inside the circuit, but it can also be different substance or liquid. Okay, if the substance or if the refrigerant that we're using inside the filler is different than the refrigerant that we're using here, it is called a cross charge. Okay, depending on whether we're using the same or different. If we're using a different, we can call it a cross charge thermostatic expansion valve. And if you look at the advantages and disadvantages and compare it, of course, to other types of expansion devices, ultimately it provides us flexibility by monitoring the temperature, a flexibility to control the flow of the refrigerant to make sure we're protecting the compressor. Okay, and of course avoiding slugging or avoiding destroying the compressor. It tends to be more expensive if you compare it to capillary tube. Can anyone think of a disadvantage? The fact that, you know, we are relying on the filler bulb. What disadvantage can you think of? So there is actually a chance if there is no a good contact between the pipe and your filler bulb, you can actually end up reading inaccurate temperatures. Okay, so there is a chance. So you have to make sure there is a very, very good contact between the pipe and the filler bulb, and you have to also make sure, you know, it's a good contact. So that's one of the disadvantage, that you may end up actually reading the temperature inaccurately. Okay, therefore, of course, driving the system incorrectly. So, and that's where I'm saying here, to reduce the influence of the ambient air, we have to make sure there's always a good contact with the refrigerant tubing. Let's recap quickly. Expansion device. By now, you should know the function of any expansion device. By maintaining a constant degree of superheat, we are able to protect the compressor from slugging, but we are also able to, by using Bernoulli's principle or by using orifice or Venturi, and I like the word bottleneck, by reducing the area of the pipe, we are able to reduce the pressure and also reduce the temperature. So when we go back into the evaporator, we are going back at low temperature and low pressure liquid. And then we've looked at the classification method of any expansion device. Two classification methods, either fixed or variable opening type of expansion devices. And then we've looked at few examples of the different types of expansion devices.